Cellular automata is a discrete dynamical system. It is having several properties, etc., etc. But today, we explore uh, other aspects of cellular automata that they can also be utilized as technology. By technology, what we mean a collection of techniques, right? So I have written the definition. So technology refers to a collection of techniques, methods, or processes used to provide some services or solution to the problems. This is wrong. To problems or accomplishment of an objective such as scientific investigation. This is the traditional definition of technology. So by technology, what we mean, some problem is given, and I'm developing some techniques. Okay, those techniques are used to solve that problem, right? And that is called technology. So it's a collection of techniques, right? Now the issue is how what we have learned till now. We have learned that cellular automata is a model of computation. Cellular automata is a discrete dynamical system, right? So it's a mathematical model we have studied. And that cellular automata, enjoy many properties, right? Right? Some cellular automata, they are reversible, right? They have some chaotic behavior. Okay. But the issue is here, we want to argue that apart from these classical things, cellular automata can be seen as a collection of techniques which will be used to solve, which can be used to solve some problems, right? And these problems, if you just simply say problem, so yeah, any mathematical model we develop to solve some problem, to address some issues. But here we want to mean that some real life problems, right? So, so some real life problems are given, and we are using cellular automata. We want to use cellular automata as a collection of techniques to solve those problems. It is strange, but because cellular automata is mathematical model, right? So, any mathematical model, from the mathematical model, we can get technology. But our argument is that mathematical model itself is a technology. So why I am saying so? Because based on this definition, that it will provide some collection of techniques to solve some problems. There are some applications which have been solved, which have been addressed using the cellular automata. First and foremost is pseudo-random number generation. So very popular one. We call it pseudo-random number generation, or PRNG. So this is one. Next important, maybe the most important, the second one, when we're talking about the VLSI, when we're talking about CA technology, that is a VLSI circuit and test. We'll see that, actually, cellular automata, in particular, one-dimensional cellular automata, they have been utilized as technology in this domain, for solving some problems related to VLSI circuit design and test. Cellular automata have been used, right? Apart from that, keeper system designs, security systems, have been designed using Cellular Automata. And another popular application of Cellular Automata is pattern classification and recognition, and other is image processing. There are many. So what I've written here, they are very famous. So first one, pseudo-random number generation, VLSI, so these are very famous. Okay. So, in this case, in this course, I want to argue that cellular automata can be thought as technology, and we cannot cover all the all applications where cellular automata have been used. So, what we'll do, we shall discuss of some sample applications. These are the. So, start with a pseudo-random number generation. So these numbers are generated by pseudo-random number generator. Okay, so we call it PRNG, pseudo-random number generator. Now, what is this? Now, pseudo-random numbers, its name is pseudo-random, right? It's not random actually. It's pseudo-random. So it should look like random, but it is not random, right? Why it is not random? What is the argument? Now, here one question may be asked: any computer, by means of any algorithm, okay, can generate random numbers? By the term random numbers, what do you understand? We understand the sequence of numbers. So one number is unrelated with other number, right? You have number one, number two, number three. So number one and number two, they're unrelated. So number two is independent of number one. That's the meaning of random, right? So there is no correlation, right? That is the meaning of random. We understand. But the question is, can a computer using any algorithm generate such number? Answer is no. Why it is no? Because algorithm, finally, it is a deterministic thing, right? So when you are getting number two, you know how to get the number two. And generally what we do, we get number two from number one, right? So if an algorithm generates a sequence of numbers, obviously there is some correlation. It has to be, because the numbers are generated by means of some algorithm, right? And in an algorithm is a step-by-step procedure. So from one step you can go other step. Similarly, when you are at some step, you can tell, okay, from which step you have reached there. So when numbers are generated using an algorithm in a deterministic process, they cannot be to the random. So what you're saying here? Pseudo-random. So computers cannot generate. I mean, computers means computer using any deterministic algorithm, in general, cannot generate random numbers. What they can do? They can generate some numbers which are looking like random. But I know that it's not random because if you follow the sequence, there is some relation. So we call it pseudo-random. Looking like appearing, as random, but not actually random. So when we talk about randomness in computer, then we usually refer to pseudo-randomness. So in my discussion, randomness means we shall mean the pseudo-randomness. well-known properties. Any query? Okay. The well-known properties of random pseudo-random numbers. Uniformity. Okay, so uniformity, independence. So I have written some only: large period, reproducibility, consistency, portability, and efficiency. What are they? Uniformity means, the numbers, you know, uh, you know, uh, uh, are to be uniformly distributed over a range, right? So if I consider, I shall, take numbers, only real numbers between 0 and 1, then I am generating some numbers. I means the generator, PRNG. PRNG, the pseudo-random number generator, it is generating some numbers. So it is picking some numbers as if. So the numbers are to be uniformly distributed. Distribution is to be uniform. Okay. So I am saying that, distribution of numbers. So as if my algorithm or my system is choosing number one by one from uniform distribution, right? And that is the meaning of randomness, right? So everything is equally probable, right? Every number, if you if you are to choose a number randomly from 1 to 100, so for example, so each number is equally probable, right? There is no bias, right? So it means the distribution of numbers is the uniform distribution. All are uniformly distributed, right? Although for simulation purpose, sometimes some numbers are generated from other distribution, say from Gaussian distribution numbers are generated, but that we are not discussing here. And while we don't mention then any distribution, then we generally consider the uniform distribution, right? And that is our intuitive understanding. All numbers are equally probable. So second is independence. Independence means, you know, so as I've said, the numbers are independent. Actually, these two are most important property. First one is uniformity, second one is independence. From these two numbers, we can get, from these two properties, we can get other properties. For example, large period. So what is the meaning of large period? So if you generate the number and the if your system is finite, you'll have a period. After generating one number, that number will come back again. Okay. So when the number which is already generated, which has already been generated, when the number will come back. The point is, it may come back, but generally it shouldn't come back. But if it comes back, then after covering a large period, a large length, it should come back. Otherwise, what will happen? The small, after a small amount of time, the same sequence will be generated, and that will not be the, this sequence will not be the random sequence. So that is the point. Okay. Reproducibility, that I'm coming to this point later, and there's consistency, portability, efficiency. So portability and efficiency is very important. The algorithm, the PRNG, by which you are generating the numbers, they should be portable. Okay. Here, one important point is reproducibility. What is the meaning? This is very important property of pseudo-random numbers. That is, if you want to generate a random sequence, you should be allowed to generate that one, right? That is, so you from one sequence of numbers can be reproduced on demand. See, this is not the property of randomness. This is the property of pseudo-randomness. If time and again you can generate the same sequence. Obviously, the generator is not random generated, right? So it shows the reproducibility. It means it implies, that um, the sequence of numbers, not random sequence, and the generator is not generating the random sequence. But this is the property of pseudo-random numbers, and I argue that in case of computing, we need this property. And I want to argue at this place that when we are talking about randomness, role of randomness in computing, then we want to reproduce the same sequence. Okay, we want to reproduce same sequence. Why? So I can give you example later maybe. Say, if you do some operation, using a sequence of random numbers, you may need after some time to do the same operation, right? In that case, you need to generate the same sequence, especially in case of cryptographic analysis. I mean, cryptographic application. Right? So you are doing some operation using a sequence of random numbers. If you do not reproduce that sequence, then the whole computation cannot be produced. In many cases, we need that one. So, reproducibility is not a property of random numbers, but a property of pseudo-random numbers, and this is essential in computing. Right? Anyway, these are the properties of pseudo-random numbers. Now we want to generate these pseudo-random numbers by Cellular Automata. How it's possible? Anyway, before that, let me tell you that Cellular Automata from the late 80s, Cellular Automata they are used as PRNG. But before that, two popular techniques were there. One is LSG. Maybe in your previous course you have covered it. Sorry, LCG, linear convolutional generator. LC is one generator. In C programming, you have used RAND, etc. RAND, DRAND, DRAND48. You have used these, generators. They all are PRNGs, and they are based on LCG. Apart from LCG, there is another popular technique that uses LFSR, linear feedback shift register, right? So these two techniques are very common techniques to generate random numbers. But here we want to argue that Cellular Automata, they are equally good to generate pseudo-random numbers, and there are many works which argue that even in terms of randomness quality, in terms of many other qualities, numbers generated by Cellular Automata, they're better than the many other techniques. Now, how can we generate such pseudo-random numbers? So, you see, in case of Cellular Automata, we generate the configurations. The simple idea is use a mapping. So, which will transform the whole configuration or some part of the configuration to a number, right? So, you need a mapping. So, you are generating the configurations one after another, and from each configuration, you are using a function. That function, transforming the whole configuration or some of the configuration to a number, and you treat that number as your desired pseudo-random numbers, right? That you can do. Okay. Historically, first cellular automata, first random numbers are generated out of ECA rule 30. Okay, ECA Wolfram's rule 30 in early 80s. Wolfram argued that rule number 30 is very good, good automaton to generate random numbers, right? So, so let me. So ECA 30 means when I'm talking about ECA, it is one dimensional, it is two state, and what's more, you know, the lattice size is infinite. Okay, see, lattice size has been considered always as usual as infinite. So Wolfram argued that if you have the system, then ECA 30 can be used to generate good pseudo random numbers. So this is a space-time diagram of ECA rule 30. What is this? So this is actually a number. A space-time diagram means I am plotting uh, uh, the configurations one after another against time. And in this case, in this particular example, what Wolfram did, he started from all zero configuration except one. Middle cell is one, and all are zero, and used to involve this. So you can see at the top, there's a single black cell. Black means is one, white means zero. So consider infinite grid, right? Then you have so all are zero, only one, and middle cell is one. I mean any cell is one. So from that configuration, you are generating next configuration. From that one, you are generating uh, the next configuration. In this way, if we continue, then you will get this one. Okay, and see, it appears to you, some randomness, some arbitrariness is there. Although you can find some similarities with some part, you can see some triangles, but some kind of arbitrariness is there in this in this diagram. So let me go back to this Jamboard just to illustrate how ECA 30 is can be used to generate numbers. So let me try. So rule 30 is like this: 0, 0, 1, 1, 1, 1, 0, 0. This is rule 30. Right. This is rule 30. Rule 30. Right. So now,
Sir,
so here, yes.
sir, rule 30 is I think 000 11110 because 101's next at 0 means 32.
Oh, I'll make it 60, right?
Yeah.
Yeah, it'll be one, right? Sorry. Yes, this is the rule 30. Yes.
Yes, yes.
Yeah, this is rule 30. Hmm. Okay. So this is rule 30. So what is done here? So I start with, so I'm using mouse to write. Uh, So everything is zero, is infinite grid. All right. So only middle cell is one. So Wolfram has studied the cellular automata in this fashion, right? Now, in now there are other infinite grid. So left and right, others are there. So now I am applying rule 30 here. So what will happen? See, since they are zero, so you understand that they will be all zero, but this part will have affected. 001, 001 is 1. So, yeah, this part will be 1, 010, 010 is 1, is again 1, and 100, 100 again 1, yes. So, these three will be 1. Then, sorry. Then, rest part will be, they will be like all 0. Just I'm writing this part. Then, what will happen? So the left part all will be 0. Just this part there will be 001 is 1, and sorry. So this will be 1 100. This part will be 1. Actually, this will increase always 1. You know, uh, you can see that each step the 1 is spreading. This is 0 1 0, 0 1 1. 0 1 1 is, it is 1, it will be 1. But 1 1 1 is 0. Here it is 0. Here it is 0. So it will be 0. 1 1 0, it is again 0. In this way, the rest part will be 0. This part are 0. So now in this way, it will proceed. Okay. So now in next step, what just the last step I am showing you, and this will be again 1. 0 0 1 it will be 1, 0 1 1 it will be 1, 1 1 0 it will be 0, 1 0 0 it will be 1, 0 0 1 it will be 1, it is 1, this is 1, yes, then 0 and 0. Okay? So here all are 0, these all are 0 here, these all are 0, these this part is 0, this part is 0, this part is 0, this part is 0, etc. Only this part, the middle part, apart from this part, you can see. So in each time, they are growing. So 0, and in this, and within that, the black part, the middle part, it can be 0 or 1. Now from this configuration, you can generate, you can generate numbers in several ways. Simplest way, we maybe, so that you consider this is 1, you may consider this number as 1, first number as 1, second number 1 1 1, it is 7, right? Second number is 7. Okay, so you're starting from here, and it is 1 1, something like it. it will be to the power 4 and 8, 20, to the power 4 plus to the power 3. What will be value? 24 plus 25. Like that. All right? So that you can do. So as if I'm using a function, what it does? So it considered this, and this part, it considered this part and transform this number as a decimal equivalent. So from this number, I'm getting some numbers, okay, and so on. So that may be my scheme, right? In this way, I can generate the numbers one by one, right? What Wolfram proposed, this is one way you can do. It is it's a good way. What Wolfram proposed, his interest was generation of a sequence, bit sequence. What he did, he started from this part, this one, and he considered this. Sorry, he considered this middle column, this column actually, this column, this column actually. So it is 1, 1, 0, 1, etc. In this way, if you I am saying by middle one, I am saying this one, this column. Okay. Now, if you start 1, 1, 0, you'll get a sequence. You get a sequence. So 1, 1, 0, 1, 1, 0, etc. Sequence you will get. So Wolfram argued that this sequence is really a good pseudo-random sequence. After doing a huge computation, it has been shown that that sequence does not repeat, right? It is like pi. If you expand pi, so there is no repetition. If you compute the value of pi, that you'll not find any period, right? If you keep on expanding the value of pi, then it will always be aperiodic. What Wolfram did, he ran this here few billion times, right? So few billion bits are generated, and then he analyzed that this sequence, this bit sequence is aperiodic, means the sequence is not repeated, right? So again and again you are getting new sequence, it is keep on going. Anyway, there is a good challenge in the domain of CA. Wolfram declared a challenge, right? He posed a question that, okay, although he ran it, so 1 billion steps, but that is again finite. Question is this sequence aperiodic? Wolfram declared a price of amounting maybe $30,000 USD, US dollar. And if you answer this question is open question, then there's a price of 30 USD, 30,000 USD, just to prove that whether this sequence is periodic or aperiodic. And experience also shows that this series is aperiodic, means, as I've said, after generating millions bits, so you don't find any period in it, right? But since it's infinite system, we don't know whether it'll have a period or not, but there is no proof. Okay, believe that people believe that, though it is it is aperiodic. I mean, it'll never get this period, but there is a proof. So therefore, what it shows? What it shows? It shows that a sequence can be generated by exploiting this rule 30 which seems to us, you know, random, right? So it's a random sequence, pseudo-random sequence. It is not repeating, right? So Wolfram argued that Rule 30 is a best candidate, is a good candidate to generate pseudo-random numbers. Okay. So using Rule 30, there are many analyses. You can see them. If you're interested, you can explore them. Right. So in this diagram, what it shows is actually the black the cells. They're the one and zero, white are zero, and it shows that from one, from single one, I have started plotting the configurations. Note that CA is still infinite. That is, you are generating 1 billion, numbers, 1 billion bits. But what is our assumption? Assumption is, it is infinite. So to generate 1 billion, to generate 1 billion numbers, in left hand side you need 1 billion cells, right hand side other 1 billion cells, right? I mean, so that the effect of I mean, you shouldn't have any boundary, right? Now, although it's a theoretical challenge that whether ECA 30, its pattern, its sequence is aperiodic or not, and no matter how good the quality of patterns is, the thing is that system is infinite. Now, if you want to implement that CA, that is not feasible. You cannot implement infinite system, right? And you have lots of burden, right? If you want to simulate that infinite system. So here we have to argue that whenever we want to consider cellular automata as technology, then ECA 30 is not very good candidate because we want finiteness. We want to implement that one in our system, right? So we want to move to finite cases only. Infinite system cannot help us much. If we want to promote cellular automata as technology, then we have to concentrate only on finite cases. So in this, in the whole discussion, uh, uh, in the whole discussion, so we shall consider that our cellular automata, the finite one. Okay. So the question is, can we generate random numbers using such finite CS? Yes, it's possible. People have worked with that, and for that, people have used maximal length cellular automata. What are maximal and cellular automata? Maximal and cellular automata are essential are non-uniform cellular automata, and its cycle length is maximal. There are many proofs. I am not going to that one. That in the classical cellular automata, in finite setting, they cannot generate maximal lengths, right? They cannot generate maximal length. So for that, we need non-uniform cellular automata. In fact, maximal and cellular automata were studied just to generate pseudo-random numbers. Okay, so first application of Maximal and CA was they explored as pseudo-random number generator. So, and in this case, more importantly, you know, linear automata, they are explored. Take an example. In this example, our popular example, we have given it before. Say it is 90, 150, 90, 150. Four cells automaton. It is non-uniform ECA. First rule is 90, second rule is 150, third is 90, then there is 150. This is a maximal cell automaton, right? So, so the T matrix of that, of that CA 90, 150, 90, 150, and right hand side is the transition diagram, right? Transition diagram, what does it mean? I have explained it before. So, let us recall that if you start from 1 0 0 0 for example, you can see here 1 0 0. If you start from there, and if it is a plain configuration, then from that you can go to the next configuration 0 1 0 0. From that configuration, you can go 1 1 1 0 configuration in this way. You'll get a transition diagram. And the beauty of this transition diagram is, except all zero, the trivial configuration, all zero is trivial configuration. All non-trivial configurations, they form a single cycle. That is, from one configuration, you can reach to any other configuration. Right? From this one, you can reach to any other configuration. So what is the length here? It is 4 cells here. So number of cell is 4, 2 state. So number of configurations possible to the power 4, 16. You can count that 15 states, 15, you know, mm, you know, 15 states, non-zero states, they are in a single cycle. So these 15 states, they all are non-trivial. Okay. Now we argue that if such a system is given to you, then the configurations can be considered as a random as a number. And from the pattern you can see, from one pattern you are going to other pattern. So from that pattern you can find a number. From that number you are going to other number. So as if from one number you can reach to any of the remaining to the power n minus 1 numbers, right? So it gives you a feeling that gives you a feeling that the consecutive numbers, they are random, right? So okay, so I can go to the Jamboard just to tell you what is happening here. So, let me copy it first. Oh, what happened? Nothing is working. Anyway, let me tell you from this figure. So here you can see that you can see, I think you can see my mouse pointer. Suppose this is your starting configuration 1 0 0 0. From this configuration you can move to 0 1 0 0. So this is This is configuration. What is the, if you just take the decimal equivalent of this number, you will get 8. From the 8, you are moving to 4. For 4, you are moving to, say, it's 12. From 12, you are moving to 15. From 15, you are moving to, it is 12. It is 14 actually. It was 14. It is 12. I'm moving to 12. From 12 to 10, 10 to 1, 1 to 3, etc. So as if, so if you write down the numbers one by one, it may appear to you, okay, so all numbers are coming one after another except all zero, except zero. Okay, it's a trivial one. You can happily exclude the zero. But except zero, you can reach to any configuration. And if you don't know the system, it may appear to you that, okay, from one number, any of the rest number is possible, right? So from one number, any of the rest numbers is possible. So as if you are picking up numbers, you are choosing numbers, from uniform distribution, from set of all numbers, and one by one, right? And see here, period is maximal. There's no repetition. Yeah, only you'll find the repetition if all the numbers are covered. Otherwise, you'll find no repetition, right? So, uh, so, so it shows that this simple argument shows that this maximal and CA can be utilized as uh, 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 as a PRNG, pseudo random number generator, right? There's the argument. Now, next, I'm showing you a theorem. So that theorem, I shall not prove it. It's a Greek proof. So that obviously I shall not prove it. But it's an interesting theorem. That, so how can I decide that a CA is maximal length or not? Point is, that can be decided easily. If so, if the CA is linear, so we are considering linear C only in this case. So if the CA is linear, then we'll have a T matrix, a characteristic matrix. Now the theorem says, if the characteristic polynomial of this matrix is primitive, then the you know the CA is a maximal length CA. What is the field here? Our field is GF2, Gauss field 2. So if the polynomial is primitive, right? So if the polynomial is primitive over GF2, then you know then then the CA is maximal in CA, and you can test. You can find primitive polynomial. How to find? So t plus ix, you find the determinant of this one. Okay, you find the determinant of t plus ix, and then that is the characteristic polynomial. If that polynomial is primitive, then so what is primitive polynomial? So polynomials are classified in two ways: reducible, when a field is given, say in any field, say in this case GF2, a polynomial is reducible if it can be factored, right? If it can be factored, then it's reducible. If it cannot be factored, then it is irreducible. Some irreducible polynomials are primitive polynomials, right? Some irreducible polynomials are primitive polynomials. Okay, so I'm not going to discuss the primitive polynomials in detail. Okay, so the point is here that if the characteristic polynomial is primitive, then if the characteristic polynomial is primitive, then the CA is maximal length CA. Okay. Is it? So I can't use Jamboard so properly. Okay. There are few more theorems that you can get, you know, you can get maximal and CS under null boundary conditions only. Under periodic boundary condition, you cannot get any maximal and CA. Same thing, same rule vector. If you take, if you consider its periodic boundary condition, proof is there that the polynomial will always be factored. The characteristic polynomial will always be factored. Means that the polynomial will always be reducible polynomial. So so hence the CA under periodic boundary condition cannot um, cannot be Maxwell and CA. So therefore, when this CA is considered, these CAs are considered as PRNG, we always consider, you always use null boundary condition due to this reason. Okay, so this is one reason, reason of popularity, one reason why null boundary condition is popular. Is so popular, right? It's one reason of popularity. And if you see the whole 90s, so most of the works, many works, they use these maximal and Cellular Automata for several purposes, right? And Maximal and Cellular Automata, for the Maximal and Cellular Automata, always null boundary condition was considered. I mean, you need null boundary condition, not periodic boundary condition. So these are the big theorems. If you are interested, you can start with literature. You can see the literature. Moreover, there is another theorem. There is not written here. I am just saying. What is that? That if you talk about um, non-uniform ECS, then out of 8 linear rules, only 2 rules, Rule 90 and Rule 150, can participate in in Maxwell and CA, right? I'm not saying that if you use Rule 90 and Rule 150, they will always be Maxwell and CA. That I'm not saying. But what I'm saying, if you don't use Rule 90 150, or say if you use Rule 160, which is again a linear rule, or 102, again another linear rule, then definitely the CA will be non-Maxwell and CA, because the polynomial which you will get, that will always be factored. Okay. So I shall not cover this theorem and proofs, etc. Okay. That will take few more classes. So what I shall do here? So while we are talking about pseudo-random number generator, pseudo-random generator, we always consider null boundary CS, right? And we use 90 and 150, these rules, right? Okay. So this is the all about Maxwell and CS and its use as pseudo-random number generator. See, next, what I want to tell you. Next, what I want to tell you that see, cellular automata, this kind of non-uniform cellular automata is very popular when they are used as technology. One important reason is this kind of cellular automata can be easily implemented in hardware that we have discussed before. Just let me revisit these things. That non-uniform ACS, the finite CS, and they can easily be implemented in hardware. Say in this kind of CA, you can see 90, 150, 90, 150, 90. It's a non-uniform CA, and it's look like this one. And each cell of the CA, can be implemented in this way: a flip-flop and a combination logic. Since it is 9150, they use only XOR logic, so combination logic is always XOR logic, right? Sometimes it is two input XOR, sometimes it is three input XOR. So this is the schematic diagram of hardware of that non-uniform CA. So when a Maximal NC is given, so R0, R1, R2, they are all rule 90 or rule 150. Okay, so accordingly, if it's rule 90, then you use XOR gate that takes input, two input XOR gate that takes input from left neighbor as well as right neighbor. And if it is rule 150, you again put a XOR gate that will take three input XOR. One will take left neighbor or from the cell, other from right neighbor. So based on that you compute, right? So this structure, hardware structure, is very attractive. We have theoretically shown that under null boundary condition, you can get a Maxwell and a CA that can generate all possible patterns except all zero, the trivial one, right? From one configuration, you can generate all possible configurations, which can easily be used to generate random numbers. And we are showing you that the whole CA can be implemented in hardware. Right? So it has another implication. You may argue that, well, when we talk about RAND, say RAND, in case of RAND, we don't need any hardware. We don't need any hardware support. So why are you talking about hardware now? Yeah, it is advantage. Especially if you want to generate random numbers for some hardware. In RAND, what do you do? We generate randoms for a program, for a software. But if you need random numbers for hardware, then your RAND function, the LCG will not work. They'll not be good. But if you see, this structure is showing that for the hardware purpose, you can easily generate random numbers, and through hardware actually. That is the implication. And so, at the age of VLSI, very large scale integration, in this case, at this age, the cellular automata becomes so popular due to it is easy to implement in hardware. And what is the most important use of this hardware random numbers? This is especially useful to test the hardware electronic circuit, right? Sometimes we want to test some circuit, right? We call it circuit under test. So to test the circuit, we need to supply some patterns, test patterns. For that, in many cases, we use these random patterns generated by Maximal and CM. Just brief about the VLSI circuit test solutions. So here you can see here a term called BEAST. Its full form is built-in self-test. It is called built-in self-test. See, when some hardware is manufactured, when IC is manufactured, right? When a circuit is manufactured, Whether circuit is okay, properly manufactured or not, you have to test it, right? What kind of faults may occur? Say very popular fault is a stuck at fault, stuck at zero, right? So I should go to the Jamboard. Let me try. What is that? Suppose I am drawing a AND gate, just AND gate. What should be the output here? If both are 1, then it will be 1. Otherwise, in any other cases, it will be 0. Does the AND gate is the property of AND gate, right? Now suppose what may happen due to some some manufacturing defect. Suppose it is always giving 0, say. So no matter what you are giving, you are getting always 0. Even in this scenario, you are getting 1 on 1, it is giving 0. Means some shorts are, I mean, some shorting is there, maybe. So this kind of fault is very dangerous. This AND gate, this logic gate, is not functioning properly. So what you are giving here? Here you are giving some 1 and 1, some pattern, right? And you are expecting in this case, it should be 1, but you are getting 0. So in a circuit, there are many such, such gates. You need to test them, whether there are some stuck faults or other kind of faults, right? So what you need actually, you need to supply to a circuit a set of patterns, right? Okay, a set of patterns, you need to give as input. And if it is functioning properly, then you know the it should be output. Then you should compare whether the desired output and received output, they are tallying on, they're matching or not. For that, again, some automated system is there. But here the point is, you need to supply, some patterns. We call them test patterns. Okay, so there are several ways of supplying test patterns. Okay, so one way is you supply the random patterns. Okay, so that I can capture a good number of faults, right? So it's a very popular technique, for testing VLSI circuit, that you supply some random patterns. So what we generate, what we need, we need TPG. We call it TPG. Stands for test pattern generator. And to implement TPG, there are several ways of implementing TPG. All for other kind of pattern also we can use Cellular Automata, that we may discuss later. But today I'm saying that for TPG we can use this PRPG. We are not calling it PRNG, we are calling it PRPG, pseudo-random pattern generator. Pattern and number, they are not same, but here since this pattern is generating, I'm calling it pattern 0, 0, 1, etc., etc. So if your circuit input, so if your input is 32 bit or say 128 bit, so use 128 CA, so Maximal and CA you may use. You generate the patterns and give the pattern as input to the circuit. So, and that is automatically tested. So that is called built-in self-test, BEAST. It is called BEAST, built-in self-test. So it is tested automatically during manufacture. So if you can put that small circuitry inside the chip, right? Then what will happen? That chip will generate the test patterns, right? You need not to supply from the outside. Generally, what happens? If you want to test, for the test, you supply the patterns. This is the general structure, general way of testing something. When you test some software, software is developed, then you test whether it is working properly or not. Debug it. But Beast is saying no. That will be very costly. Beast technology is saying that will be very costly. Rather, to make it very cost effective, put a small circuitry inside the main circuit, so that during manufacture, after manufacture, I mean during the manufacture of the main circuit, that test logic will be manufactured, and then it will automatically generate patterns, and automatically it will be tested. If any error is found, it will be rejected, right? That is called beast, built-in self-structure. For the beast, PRPG can be used. So cellular automata based PRPG can be used, right? Why it is so? Because it is it is easily implementable in hardware. It demands low space, okay, and it has other advantage, it's scalable, etc., etc. So, for VLSI circuit design, this kind of maximal and cellular automata they are used. So, when you're talking about technology, so this is an example of technology, right? A problem is there, you have to test the circuit. For that one, you use maximal length cellular automata as your test pattern generator. Okay, and that's all for today. So, any question?
Sir, how is this tested?
Which one? I-
This
How it is tested?
yeah, how PRPG is used for test.
Okay, so suppose this is the PRPG, this small circuit you can see, right? You can
Hmm.
see it. Okay, so here output. Uh, so you can see. Can you see my mouse pointer?
Yeah.
Okay, okay. So this output, right? The output so for from cell zero is one output, cell one another output, etc. I can get n outputs, n bit patterns I can get. There's 0 1 0 1 etc. Some pattern it is getting. I'll get that pattern will be input to the main circuitry, right? So that pattern will be generated, and now if some fault is there, I know what is expected behavior in that case. That circuitry I also put. So this is I am saying that C is for the whole beast, C is not used. Just C is used as TPG, test pattern generator, which is the most important thing. See, most important thing is test pattern generation. If you have n bit, suppose if you have 62-bit machine, say 64-bit machine, right? So there are several patterns are generated, you know, and if you want to exhaustively test them, then to the power 64 patterns are there. You have to input them. So how can I input them? If you think that you will put them in, keep them in some file and then fit one by one, it's impossible, practically impossible.
Hmm.
But what your Maxwell CA can do, well, you you give some initial pattern, right? There is prefix, right? And then prefix means that is fed into the system actually. Hmm. So then it will generate the one by one patterns, right? So the idea of beast is like this. Before the concept of beast, how it is tested? Some files are there. Externally, you have to separate the patterns, right? So, but here you have the small circuitry. The circuits are generated the patterns, and then patterns are going to the main circuit. Now you know the behavior, and that's not the end. Just giving the giving the input is not the end. So you know, say 10010, etc. If it's the input, then what is the correct behavior that you know? That is true for all all circuits. So, for example, one processor is being manufactured. So, for that processor, for a particular pattern, output will be all will be same, right? But if it is found that for some device, some manufactured, some device, some chip, its output is different. For that circuit is this. Again, that is analyzed, right? Some signature is taken from that. For that, another circuit is there. So if it is found that the expected output and they are not matching, then the whole chip is rejected. Okay, as default, is rejected as faulty one, marked as faulty one. I
Okay.
mean, maybe you're not satisfied. I mean, what is the question? I mean,
No, I was thinking that this PRPG that will generate some random pattern, but how we will know what pattern is generated and if we don't know the pattern?
okay. This is the question. So there are three types of pattern generally. Uh, Called one is called deterministic pattern generator. For that also CA can work finely, work fine. For example, I know the most difficult and these are test patterns. I know. Sometimes some benchmark circuits are given, and for that, sorry, I know that these kind of test patterns are essential for the testing purpose. That is called deterministic patterns. So therefore, your beast, your test pattern generator, has to generate that set of patterns. That is one technique. That is called deterministic test set generator, DTSG, or DT. I mean, sometimes we call deterministic test pattern generator. That we know. Okay, but that is the good one. But the problem is, by doing that one, you may capture the major faults, but not all. Right? See, deterministic test pattern we always need. For example, we do not allow any kind of staggered fault because that is dangerous. For that, I need to supply a deterministic set of patterns. But that is not the end of the scenario. That is not all actually. So you test it completely to make it complete test. What you practically need? You need to supply exhaustive patterns, right? So if it is machine or 64-bit machine, so you need to supply to the power 64 patterns. That is not very practical. Okay, but we can argue that even then I can work with this, with the pseudo-random number generator, because in my design it can generate all the patterns. But what is done here? That will take much time. Now, if I want to supply all patterns, what we do, we generally supply say 10 to the power 15 number of patterns. Okay. Now, what is the role of good PRPG? Its role is, see, I am expecting, since the patterns are generated randomly, so I'll be able to capture major faults. Okay, it is not that. If I supply say 10,000 patterns or say 30,000 patterns, by supplying 30,000 pattern, I cannot ensure that all possible faults I have captured. No. But if my pattern generator is very good, and it is really capable of good random patterns, then there are some faults called uh, random resistant fault. What is the name of that one? I mean, some faults which can be captured by supplying such kind of random patterns. Suppose there are 10 patterns, 10 such, 10 such errors, 10 such faults, and you are generating random patterns. And you are showing that out of 10, 8 patterns you can generate by your system, by your PRPG, after generating 100 patterns. Okay, that's good. Okay. Uh, then that is, if I supply only 100 patterns, then out of 10 faults, I'll be able to capture 8 faults. Okay, so that was the challenge actually. By LFSR and Cellular Automata, and many authors they have shown that LFSR cannot capture all the faults or such faults. But while you are using this PG as your TPG, then you don't expect that you'll be able to capture all the faults, right? And very interesting, if you look at the distribution of the faults now, if you even draw the transition diagram of CA, you will see that they are clustered. Okay, they are randomly distributed over the space. Okay. So that is the strength of your design, that okay, you'll be able to cluster them and etc. etc.